this. And let's look at the first set of slides, which is precision and recall. Okay, so this has been happening. My computer is freezing now, and I'm just going to wait for it to unclench. Still, you guys doing okay? Can you hear me still? Okay, okay, good. So, all right, I think the crisis is over here. All right, so the first thing that we're going to talk about is precision and recall. Um, so there's this funny thing that happens if you have an unbalanced data set. So some data set where positive instances are much more common than negative instances, or vice versa. Then if you use accuracy as your measure of performance, then you can get models with really high accuracy that are just dumb, like in the case of predicting a rare cancer from a photograph. A model that just always says no will have high accuracy just because there aren't many cancers out there in the population, but it isn't doing anything, and it's gonna kill people. What you really care about in that case is not accuracy, it is avoiding false negatives. So there's various versions of that we're going to talk about as we go down through here. This is the thing that I butchered at the end of class last time. I've got to tell you, I have some kind of brain defect that impedes my ability to deal with symmetries like false negatives, false positives. It frankly confuses me. Okay, but so precision is if you say that an instance is positive, it's the probability that you're actually right. So precision is the frequency with which a model is correct when it reports an instance to be positive. And then if you want to express that in terms of true positives and false positives and stuff, so TP here means true positive, FP means false positive. So the denominator here is all the times that you said something was positive, and the numerator is all the times that you're actually right. So the way that you maximize precision is by having a very high bar for when you flag something as a positive instance. Like it's supposed to be in court, everybody's innocent until proven guilty, or it's better that 10 guilty men go free than one innocent person be hung, or something like that. So that's like a traditional value in the American justice system. So that's a high precision standard. So in this case, being positive would be being guilty. So you want to have very high precision, and as a consequence, you're going to let a lot of guilty people go away. But that's okay. Just if you value, if you're more horrified by punishing the innocent than by releasing the guilty, then that is the desired behavior. And another case here I stole from hands-on machine learning. It gives the example of a net nanny. So some people have like filters on their home internet or something to stop their kids from looking at all the awful things that are out there. You don't want your 5-year-old looking at red rooms on Tor. I've been told those don't actually exist. But anyway. So with a net nanny, it might be okay if you lose out on seeing a lot of good websites, as long as you protect your child from seeing something awful. So it's better to not, it's okay if you lose some good websites, if in return you can be confident that your child isn't going to see murder or something like that. Yeah, so when do you want to be, I don't know, this is my own editorial sentence here. When do we really care about precision? It seems to me it's usually when we're thinking about taking some action that might be harmful, if it something that we have to be really sure before we act, like killing somebody, or sentencing somebody in court or something like that. Okay. So recall is the fraction of instances that really are positive that get reported by your algorithm. Here comes my daughter. Um, TP is true positives. Um, recall only deals with positives. So all positives that you report are true positives. So this is everything all the positives that you report, the things that are actually positive that you detect, divided by the number of positives that are actually out there. So this is the fraction of things that really are positive that your algorithm is able to detect. So you maximize recall by having a very low standard for when something is a positive instance. Um, so, you don't, um, all you care about is making sure that you detect all the positive ones out there. If you say that something is positive and you're wrong, recall doesn't care about that. It just cares about making sure that you point out every single positive instance. Um, so you see this in like hands-on learning, and with scikit-learn and TensorFlow gives the example of a shoplifter. So if you're running a department store, and you're trying to automatically detect shoplifting, you might have a very low bar for when some customer activity gets flagged and referred to security. Um, when this happens, maybe 9 out of 10 times the person is not doing anything wrong. And you just want to be sure that you do detect it when shoplifting does occur so that you don't lose any money. Usually the false alarms can be followed up manually or something. You just want to cast a really wide net. The same thing applies with detecting cancer. So in detecting cancer, you want to minimize false negatives. So it's better to have a false positive than a false negative. So you want recall to be high in things like cancer detection. Yeah, so when you're trying to detect something dangerous, if there's a possibility that you miss something and it ends up killing you, then you want recall to be high. Um, and this is sort of like in human psychology. This is why we're scared of the dark and like bumps in the night and things like that. It's because it's better to have a low threshold for detecting like a cougar in the bushes, because if you're wrong, it doesn't matter. Well, if you're wrong, then you die. But if it's a false alarm, then who cares? You get a little bit scared. Um, but if you fail to detect a true positive, then it eats you. So a common way of balancing precision and recall is called the F1 score. So it's not it's not the answer to the problem of balancing precision and recall ideally. Because in some situations you want to have really high precision at the cost of high recall. But if you want both precision and recall to be pretty good, which is sort of generically what you want, you want both precision and recall to be pretty decent, then F1 is a good way to measure how close you are to doing that. So it's just the harmonic mean of recall and precision. Yeah. Okay. So let's do a real example with the handwritten, the MNIST data set, the handwritten digits. So there they are, just to remind you what they look like. I did something, so I'm just doing I'm looking at threes. So the data set is a multi-class classification problem because there are more than, it's not binary classification because there are 10 digits. But I turn it into a binary classification problem just by changing y so that it's 1 if the digit is a 3 and it's 0 otherwise. Normally we use +1 and -1 when we're actually doing the math, but I'm just using sklearn library here and it can handle 0 and 1. It doesn't care. So I use a logistic regression model, and I did something dumb. I didn't scale the data, and that's why it's not converging here and it's yelling at me. So it could be, the performance could be better if I scale the data, but I was just too lazy. And it doesn't really matter for our purposes here anyway. So I train my 3 detector, and then I look at the confusion matrix. And so just to remind you, this is we talked about a confusion matrix last time, but just in case you missed it. So here the rows are the truth and the columns are the prediction. And 0 means not a 3, and 1 means it is a 3. So 15,631, those are the non-3s that are correctly reported as non-3s. But over here are some non-3s that are falsely reported to be 3s. So those are false positives, you can see over here. And down here, this is when the prediction is 3, but 286 times there are things that are not 3 that are reported to be 3. Wait, no, this is things that truly are 3 that are reported to be non-3s. So those are false negatives. And here we have the true positives. So those are the 3s that actually were reported to be 3s. So notice that about 10% of the data actually was a 3. So that's the distribution in this training set. Each digit is about 1/10 of the data. Okay, so you can actually get true negatives, false positives, false negatives, and true positives right out of the confusion matrix, and here they are. So you can just use the formula that we gave to see what the precision is. It turns out to be 90%. That means when we say something is a 3, we're right 90% of the time, which is pretty good, I guess. You can also just import precision score from the sklearn library, and it gives exactly the same value. So similarly, here is recall, just from the formula for recall that we gave above. And it turns out to be 83%. So that seems like maybe not so good. So that means of the 3s that were out there, you only found 83% of them. And here's the recall score from the library. If you just get the model score is the accuracy. So notice that you would sort of like, this is about 98% accurate. So that sounds great, but it's not as good as it sounds because only 1/10 of the data is actually 3s. So this is kind of misleadingly good. And the F1 score says to what degree our recall and precision kind of balanced in the performance of the model, and you get a score of 87, about 0.87. Okay. So I wanted to see some examples of false negatives and false positives here. So these are the false negatives. So these are the ones that really are 3, but the model failed to detect them. And I don't know. So to a human brain, these things are obviously 3s, but the logistic model is just a linear model. So for each pixel, it assigns a coefficient, weight, and stuff. So I think what's happening here is there are certain pixels that the linear model pays attention to. Those with high weights, and these 3s kind of have weird placement, and they're not hitting those those pixels for which the weights are high. It's missing those. And here are the false positives. So these are things that are not 3 that are reported to be 3 by the model. A lot of them are really awful, really awfully written. But here's the opposite problem. So the logistic regression algorithm is paying attention just to certain pixels here, and these numbers are hitting all those sweet spots. So it's like triggering it, just because part of the number, a lot of it lies on those high weight pixels. Okay, so how do you trade off between precision and recall? So we said that you could make precision go up by being more particular about what you report as positive, And you can make recall go up by being less particular about what you report as positive. So that it is a trade-off. As precision goes up, recall goes down, and vice versa. And logistic regression gives a nice way to trade off between the two, because remember, logistic regression, it really estimates probabilities. And then usually we just, we threshold those into predictions. So, by default, we say that the prediction is true if, or we predict 3, if the probability is greater than or equal to a half. But we can change that threshold. And if we make the threshold go up, then it becomes harder to be classified as a 3. If we make the threshold go down, then it becomes easier to be to be considered a 3. So here I get the probabilities from the model, and it comes with 2 columns because it has the probability of 0 and then the probability of 1. But it's redundant because there are only 2 possibilities, so you just need 1 column of those. So I get the column that is the probability of being a 3. And so now I make a new set of predictions, and now I'm saying that something is a 3 if the model estimates that the probability that it's a, if the model estimates that the probability of it being a 3 is at least 25%. So that's lowering the bar to being a 3. That makes the accuracy score go down. That's not really surprising, because now you're going to be saying that some non-3s are 3s. It makes precision go down because you're letting in all kinds of crap. Somebody have a question? You're always welcome to talk over me. But it makes the recall score go up because now we're flagging more of the 3s. So before we were only flagging, I think it was like, was it 83% or something, some pretty small number. Before the recall score was like 83, 84%. But by lowering that threshold, we made it go up to about 91%. And the opposite happens if you push this up. So now if I push the threshold for being considered a 3 up to 95%, precision goes up really high, but recall goes down to just 50%. So now we're leaving about 50% of the 3s on the table. But when we do say something is a 3, we're right about 99% of the time. And this makes F score go down too. So which one is right? It depends on the problem. In this case of optical character recognition, I would be happy just maximizing the F1 score, because I don't really know why we should prefer high precision to high recall or anything like that. So let's look at some plots. So we're gonna, this first one is recall as a function of the threshold. So if you make the threshold for being a 3 0, then of course you get all the 3s. If you make the thresholds for being a 3 1, then you get none of the 3s, I guess because the model is never completely certain. And actually I cut off those 1s anyway because I didn't want to be dividing by 0 or something. Okay, so as the threshold goes up, recall goes down. And the opposite is true for precision. So if you have a very low threshold for what's a 3, then your precision is going to be terrible. It should really be 0, ideally, but it starts out at 0.1. But I didn't actually evaluate what happens when the threshold is 0. We could see what happens if the threshold is actually 0. Then precision is still 10%. So I don't really get it, to be honest with you. because everything is greater. Should I change this to greater than or equal to 0? That might do it. No, okay. So honestly, I find this confusing because this should be saying that everything is a 3. So if it's saying that everything is a 3, okay, you still have some non-zero precision, right? Because you're still going to be somewhat right, you know? So some of them really are 3s. Okay, so that makes sense. And also this is about 10%, which makes sense because about 10% of the points in the data actually are 3s. So that makes sense. Okay. Okay. So that's precision as a function of the threshold. And here's F1 score as a function of the threshold. So this reaches a maximum at some point. It looks like probably around like maybe 0.45 or something. F1 is maximized. So now let's look at recall as a function of precision. So these graphs are kind of interesting because in an ideal world, for any precision score, the recall would be 1. If you had like a perfect classifier, then for any level of precision, the recall would just be 1. And this curve would look like the upper right-hand corner of this curve. And then the area under this curve would be as big as possible. It would be 1. So one way to measure the quality of a model is the area under this curve, and then comparing that number to 1. And that is we're gonna get to that. It's just that it's more common. Instead of using this curve, we're going to use a slightly different curve called the Roc curve. And Roc curves, ROC stands for receiver operator characteristic. So this is totally like 40s or 50s kind of terminology, I guess. I have no idea why they called it that or what the history of this concept is. But it plots the on the y-axis of the Roc curve, there is what they call the true positive rate, which is the same thing as recall. And on the x-axis is what they call the false positive rate. And again, the symmetries here just make my head spin around, and I find it really hard to keep it all straight. But so the false positive rate is false positives divided by the number of negatives. So this is the true number of negatives. So one way of thinking of that is it's the probability of false alarm. So every time you say that it's positive and you're wrong, that's a false alarm. So as the probability of false alarm goes to 1, recall also goes to 1, and that's because as the probability of false alarm goes to 1, you're just every negative will be a false positive. So you just have to say that every negative is a positive. And then that makes the probability of false alarm go to 1, and it also makes recall go to 1. And it's also true that as the probability of false alarm goes to 0, recall goes to 0. So this one is less clear to me, I'll be honest. But I guess that's because fewer positives are predicted. So the only way, I guess, to make false alarm, the probability of false alarm go to 0 is to predict fewer positives overall. And that will also make recall decrease. So here's the library call here to get the Roc curve, and it gives you the false positives, the false positive rate, and the true positive rate, and the thresholds here. And then this code I just copied verbatim out of this book, Hands-on Machine Learning with Scikit-learn and TensorFlow. And so we get the Roc curve here, and they also plot the diagonal. And the significance of the diagonal here is, let's just say that you made a model that randomly classified things. So flips a coin doesn't look at the data at all and then decides what the category is, then that model would be along the diagonal here. So the difference between the actual Roc curve and the diagonal is a measure of how much much superior your model is to just making random decisions. And if it were a perfect model, then this blue curve would be pretty much the same as the axes here. So it would go straight up until it got to 1, and then it would go straight over. So for a perfect model, the area under the Roc curve would be 1, because it would just be the same as the area inside this 1 by 1 square. So the difference between the area that you actually have under your Roc curve and the area of the square is called the Roc, which is the area under the Roc curve. So ROC, receiver operator characteristic, area under curve. Silly terminology. But a perfect model will have a Roc of 1, and a random model will have a Roc of 1/2. So for, and notice that it needs to take the probabilities. And so we get a Roc score of about 0.98 here. So this will happen sometimes if you get really interested in doing contests on Kaggle. Often they say the winner will have the highest Roc score. So then what would you submit? What do you submit so that they can evaluate your Roc? You have to give them not your predictions, but your probabilities. So it's your probabilities, and then they can, once they have your probability vector, they can apply different thresholds and build the Roc curve from that. So the vector of probability estimates it's a lot more informative than just your vector of predictions. So let's just put another curve on there, and I'm just exactly copying the book here. So I get the random forest classifier. This thing can also predict probabilities. So I get the probability vector from the random forest, and I plot them both on the same frame here. And it turns out that the random forest does better than logistic regression. But remember that I didn't scale the data, so that is not a super fair comparison, because that hurts logistic regression, but it doesn't hurt the random forest. And the random forest gets a Roc score of almost 1, so it does really well. And so that's pretty much it on this slide set. Any questions about those?
Professor?
Yes.
If you do scale it, is it going to hurt the random forest one?
No, it's not going to hurt the random forest. We'll hopefully, I want to get to neural networks and decision trees. So hopefully we can, I think neural networks will take a week probably, and then maybe decision trees we can do in a day. I'm not sure. But we'll do both of those before the end of the semester, because random forest is, a lot of people just use that straight out of the box, and like scientists, you'll see papers and like if you look on PLOS One or something, if they're doing machine learning, often they just use the random forest and don't even try anything else, because it does tend to work really well out of the box. And neural networks obviously are super important because of self-driving cars and deep fakes and everything that's going on with neural networks. Also, voice transcription, automatic translation, all of those things are using neural networks. Okay, so let's go to multi-class classification. So this is kind of, before we have the we had the MNIST data set where there were 10 possible classes, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that we could use logistic regression, we broke it down into a binary problem, just whether or not the character is a 3. But what if we wanted to do multi-class classification? on a data set like MNIST. So you know, when you guys did project one, a lot of people picked data sets that were non-binary classification. There's, you know, a lot of that out there. So some algorithms do it naturally. Like in last class when we studied k nearest neighbors, we saw that k nearest neighbors just, you know, if you take the mode of the k nearest neighbors, then that automatically is a multi-class classifier, so it doesn't require any extra work. And decision trees, random forests, you know, forests are ensembles of trees. Um, decision trees are also naturally multi-class classifiers, and so is naive Bayes. I don't think we'll get a chance to talk about naive Bayes. And neural networks also. Okay. But we've mostly been studying linear models in this class, because I think this, once you get out there and get into sklearn, you can use all the models. You don't really need to understand how they work, but what you do need to understand is how to avoid overfitting. So that is that's mostly what we've been talking about in the class, because I think that will help the most if anybody wants to go out and do real data science. But these things where you have like a decision boundary, like linear models and support vector machines, they're naturally binary classifiers because you're either on one side of the line or the other side. So here we're just going to quickly go through how to use binary classifiers to do multi-class classification. And there are two basic strategies. The first one, which is sort of generically the preferred one, is called one versus all. Sometimes also called one versus rest. So let's say you have three, I stole this slide and I'm sorry, I don't know who created the slide, but I'm grateful for having it. And so there are three different classes here. There are these little hexagons, circles, and diamonds. So in one versus all, you make one classifier to do hex versus rest, and you make one classifier to do diamonds versus rest, and you make one classifier to do circles versus rest. And like if we were to do this strategy with the MNIST data set that we were just looking at, we would make 10 models. One model would be 0 versus non-zero. Another model would be 1 versus not 1, 2 versus not 2, and then up to 9 versus not 9. So for every class, you have one classifier. And for this to work, each classifier has to be able to produce some kind of confidence score. So most models can one way or the other. The logistic regression does it really naturally, but there are ways that you can force pretty much everything to produce some kind of confidence score. And now what do you do if you want to classify a new image? So you look at all the models that so every model you have a new image, and now every one of these models makes a prediction. So some of them are going to say yes. Like I show a new image of a number, and maybe 1 and 5 and 6 all say, yes, it's a 1. Now the other one says, it's a 5, and the other one says, it's a 6. And all the other models say, no, it's not me, whatever. So then of those that say yes, you pick the one that's the most confident. So maybe 5's probability estimate is like 0.99. And then for the other cases where the answer was yes, the probability is less. So you take the model that says, yes, it's my type, that's the most confident. So, things can go wrong. Like what if everybody says no, or, stuff like that. But in general, it works pretty well. Okay, so here's,
Is there
sorry.
is there a limit to the number of classifiers you can have for like something like that? One versus all?
No, but there's a cost. There's like, and also every one of these has to be trained on the full data set. So for MNIST, you have like training on MNIST takes a long time because there's like 70,000 images or something like that. So each one of these classifiers has to be trained on a data set of size 70,000. So it like, you have to do all the work 10 times. And so there might just be a limit to how long you want to wait or how long you have to wait or something like that. But there's no reason you can't have, like in the abalone data set. I don't know if you guys remember that. That's like the number of rings in the shell of an abalone. So that's a case where you like both regression and classification makes sense because I think the number of rings goes from like 0 to 30. So on the one hand, it's just 30 definite classes, but on the other hand, they go continuously from 0 to 30, and there are quite a few of them. So if you were going to do classification on an abalone, then you could use this strategy, and then you have to have 30 classifiers, one for each number of rings. But there's no reason you can't do that if your computer has enough memory. Here I finally got around to scaling the data, and you can see logistic regression just converges right away, no problem. The sklearn library classifiers, they use OVA by default, except for support vector machines, is what I've read. So this logistic regression uses OVA strategy by default. And so I'll see, okay? So we train it, and now let's take one test point. So I just take the test point that's in the first position here, and we want to predict it. But I predict its probability. But look what it returns. It returns not one probability, it returns 10. What do you think the meaning of these 10 probabilities are?
For all 10 of the numbers?
Yeah, exactly. So there are actually 10, it's doing OVA, so there are really 10 classifiers. And so the first classifier is the is it zero classifier. And so that classifier says that there's a very small chance that it's 0. And this number corresponds to the is it 1 classifier. And this also gives a pretty small chance. This is the is it 2 classifier. This is the is it 3 classifier. Is it 4? Is it 5? Is it 6? Is it 7? Is it 8? Is it 9? And it turns out that the, oh, look at this. It's actually, it's a little, oh, okay. So it's like 9, it's 8 times more certain than it's 9, that it's 9 than this. Its other best guess would be that it's a 3, 0, 1, 2, 3. So both 3 and 9 get pretty high probability estimates, but 9 it's much more certain that it's 9. So it predicts 9. So this is just the prediction that the model makes, and it's doing it according to this algorithm that we just described. It's basically picking the argmax of the probability vector, which is it's just saying that the highest number is in the 9th slot. And I never did actually look at why test 1, but I guess we could. Ah, bastard. I think that might be for something else, because I just ignore that. Because I'm doing some other stuff down below, so it's probably a different test set. Okay. But at any rate, whether it's right or wrong, that's how it makes its prediction. Okay. And if you look at the performance, I actually did scale the data, so I can delete that now. So it's 91% accurate, which is pretty impressive because it's not binary classification anymore. For each time it makes a prediction, it's saying which number it is. So to do that correctly 90% of the time is pretty impressive. Okay, so it does have some downsides. One is that each model has to be trained on the entire data set. And for MNIST, you know, that takes a long, long time, like minutes on, maybe 10 minutes on my machine, or a couple minutes at least. So you also have, so why does this, why does sklearn not use this strategy with the support vector machine? So we've said earlier that the support vector machine scales very poorly as the number of rows increases. The training time increases as the cube of the number of rows. So for the support vector machine, it would be better if instead of training on the entire data set, you could train on smaller training sets. And so this is the upcoming idea here, one versus one. So we'll come back to that idea in just a second. Another problem here is that almost all instances will be negative for each of the classifiers. You're training 10 classifiers, but each one of those classifiers is looking at fairly unbalanced data, because for each one of those classifiers, the true positives are only, the positives are only 10% of the data. So you might get weird behavior, like, you know, a bunch of lazy classifiers that just always say no and are right 90% of the time. You know, what if every classifier does that? Okay, and another weakness is that you have to have some way of producing a confidence score, but most models have some way of producing some kind of confidence score. Okay, so the other strategy is one versus one. And so now you'll notice that in these pictures, so now there's a classifier for each pair. So there in both cases here, there are 3, but that's just a weird thing about 3. You know, here there are 3 possible classes, and so we make one classifier for each class, so that means 3. But in one versus one, we make one classifier for each pair of classes. And it just happens that with 3 classes, the number of pairs of classes is the same as the number of classes. So it also happens to be 3. But in general, this number is much bigger. Like in MNIST, if you use this approach with MNIST, you have to compute 10 choose 2 models, because you have to compare. One model is going to be 1 versus 3. Another model is going to be 4 versus 5. So there's a lot of ways to do that. So in this example, you have to train 45 models on the MNIST data set, which is still possible, but it's a lot of models. The good news is that you don't need to use all the data. So let's say that you want to train a model that's going to compare 0 and 8. So you only need the instances that are relevant to 0 and 8. So that's like 20% of the total data. So each one of these 45 models is only training on 20% of the total data. So even though you have to make more models, each one of those models trains on a lot less data, which can make these things kind of equivalently fast. I did a little, like I did this calculation here. So if you do one versus all, you have to do 10 classifiers, and they all train on the entire data set. So that's 10 times n amount of work. But if you do on this data set, you do 1 versus 1, then you have 45 models. But for those 45 models, each one trains on only 20% of the data. So that actually turns out to be a less work, quote unquote. You know, this is a pretty rough way to do the calculation, but you know, by this metric, it's nonlinear. You know, like the support vector machine will have to do 10 times n cubed work, whereas here the support vector machine will have to do you know, n over 5 cubed times 45, which is going to be a smaller amount of work probably, because the cube is really sensitive to big numbers. But anyway, the strategy here is just make a bunch of models, and there's one model for each pair of classes, and what that model does is distinguish between those 2 classes. So now what do you do when you have to make a prediction? You just you give the new instance to each one of these 45 guys, and each one votes on what they think it is. You know, so the 0 versus 1 classifier, it just votes 0 or 1. And the 0 versus 2 classifier just votes 0 or 2. The 9 versus 8 classifier just votes 9 or 8. And so the idea is the class that's the actual truth will get the most votes. And so, you know, yeah, so as long as these things work fairly well, let's just say that you give it a new instance and it's a 3. So most of these classifiers don't have anything to do with 3. So of the ones that do have to do with 3, how many is that? There are like 10 of these that have to do with 3, right? So all of those 10 presumably will vote for 3. And then the other classifiers that don't have anything to do with 3, it's going to be like a coin flip. So like 50% of them, they'll just vote for other numbers at random. So 3 will have like an extra boost, which is the 10 votes that it gets from the 10 classifiers that actually do involve 3. And then for the other classes, it's going to be sort of like random noise. Okay. So here you can actually get the estimators, and if you wanted to, you could go through here and make these estimators vote. You know, you could just make each one of these 45 things do a prediction, and I probably should have done that, but I didn't get around to it. Is it too late? Can we do like for model and OVO estimators? Let's just see if this is even listening to me. Okay, so we could do that. And so let's make something that we want to predict here, like X test 1. And so we'll do, hello, how are you, honey? Good. So the prediction is going to be model.predict X, and then we'll do votes.append prediction. Okay, and then we'll look at the votes at the end. Okay, so these are the predictions, and crap. Unfortunately, I don't have any way of knowing which pairs each of the you know what I'm saying. So each one of those models is for a certain pair of classes, and I just realized I don't know which model corresponds to which pair. So I don't know what the meaning of these votes are, in other words. So, but each one of them is voting for something, and then presumably, if you count up all the votes, then they will be voting for the correct answer. So that's all I had to say about multi-class classification. Anybody have any questions about that? Okay, so now we're going to go on to talk about cross-validation. So the I'm basing these notes on our textbook, Learning from Data. So let's go to Journal here, and let me just start with a new document. Okay, so how many people have heard of cross-validation before? So before we talk about validation, maybe we should just quickly talk. So what's the difference between, oh my God, sorry. This happens sometimes. I think if I restart this application, it'll be okay. So I just restarted it, and now I will share it again. Sorry. You guys have professors with a lot of technical problems, or just really been like plagued by them? Okay, so it works now. Okay, So let's talk about the idea of a validation set first. So all throughout the semester, we've been breaking things down into a training set and then a test set. And the point of the training set is to produce some, best, hypothesis here. The point of the test set is to estimate the out of sample error. So E-test of G here is supposed to be roughly the same thing as E out G. So this is the, remember that E out G is the true out of sample performance of the hypothesis. But lately we've been doing something which we probably shouldn't do. Instead of just considering one model, we've actually been considering a lot of models, and and the difference between these models is usually the choice of a hyperparameter. So like when we're doing regularization, for example, if you want to call the regularization parameter lambda, we don't just have, we have like a whole bunch of these, like we have one model for each choice of the hyperparameter lambda. So often we have like 3 or 4 of these things, but let's just say we have 3 of them. So what we've been doing is we've been training these on the training set. So we do. So here's, this, they all go through this sort of training phase, and then after training, they produce some sort of best hypothesis here. So let's call this G1. This one is G2, and this one is G3. So they all go down, and we see how they perform on the test set. And then one of these will do the best. So it will have the best performance on the test set, and we call that like G star or something. Okay. So then we decide that whichever family G star came from is the best choice of the hyperparameter. So let's say that G star, the model that did the best on the test set, came from this model that had this choice of hyperparameter. So now what we've done, this is called model selection. And this makes a lot of sense, because you've seen by what we've been doing, that choice of hyperparameter can make an enormous difference on performance. Like you're doing that right now in your 4th homework. So it could be the difference between like 97% accuracy and like 50% accuracy or something. So we have to do this. But the problem is that we're kind of abusing the test set. So the test set is not really supposed to be for that purpose. The purpose of the test set is supposed to be to estimate the out of sample error of our best hypothesis. And the quality of this estimate here relies on the fact that we're only putting in one hypothesis here. So I don't know if you remember the stuff we did earlier in the semester with the Hoofding bound. But when you're trying to use data to approximate some parameter here, if there's only one candidate, then the estimate is much better than if you're choosing like the best of 3 candidates here. So here we're choosing the best of 3. So that's making G star extra lucky, and that extra luck is going to sort of corrupt this approximation here. So the validation set is kind of like the test set, except that the purpose of the validation set is not to predict how close, it's not to predict the true out of sample error. The point of the validation set is to pick the best hyperparameters, or pick the best model. Okay, so how do you do that? So now we usually are just desperate for data. So now we're supposed to have a training set, and we're supposed to also have a test set, which is about 20% the size of the training set. So now they also want us to keep a validation set around, which you can do, but it has a cost, you know. So now you're only training on, I don't know, what do you want to call? So something has to go down. So if these are both like 10% of your data, now you're only training on 80% of your data. I guess that's what you were doing before. But now by reducing the size of your test set, you've made the variance of your out of sample error go up. And so you're going to be more wrong about that. Also, this thing is kind of small, so you might end up picking the wrong hyperparameters too. So a solution to that dilemma is something called cross-validation. And the simplest version of this is, let's just look at leave one out cross-validation. Okay, so so in this situation, we're going to have just X train like we normally do, and we're going to have X test over here, which is still a full 20% of the data that you have. And with leave one out cross validation, we're going to, so for each X in the training set, so X train, we are going to train a model. So this is for whatever hyperparameter we're considering or whatever. So we do this whole process for each hyperparameter. So for each hyperparameter, for each training point, we train a model on X train. This is set minus here. I don't know if you guys have ever seen this before. Oh, oops. So this means the training set without little x here. So we train a model on everything except for little x. So we don't train on that. We just train on everything else. And then we use this to make a prediction y hat about little x. Okay, so we do that for every x in the training set, and that gives us a prediction. It's a whole lot of training, right? It's one model for every point in the training set, which is going to be expensive, but let's just assume for the time being that we can do that. Then we get sort of a, I've already said y hat here as if it weren't a vector, but now I'm going to abuse notation. So I'm going to consider this to be y hat is a vector of predictions about each training point. Okay, and so you can evaluate that just on versus, so you can compute the error. So what is the error of actually, you know, we can put a little CV here for cross validation. So then what is the error of y hat CV versus y train? So we have these are the true values for the training set. So we can evaluate that error. And it turns out that this is a pretty good estimate of the quality of the out of sample error of sort of H lambda. So H lambda is this model that you're considering that uses this hyperparameter lambda. This is going to be a decent estimate of the out of sample performance of the best G in H lambda. Okay, so we do this for every lambda. We record you know, this value, and so let's call this like E lambda or something. And then after you've done all that, you want to pick a model. So the model that you pick, sort of the winning model, is going to be H lambda, where lambda is the argmax over all lambda naught here of the error of YCV lambda, so the one that's computed from lambda, and Y train. So I know that my notation is probably not the greatest, but everybody get the basic idea? All right. So to give an example, like let's say that we're doing the support vector classifier. And so the support vector classifier with RBF kernel, it has two hyperparameters, C and gamma. So you know, C is how much the support vector machine hates slack, and gamma is how far the influence of each support vector extends over the other points that are being considered. I hope you remember the RBF stuff that we did last time. So gamma affects like the sort of the steepness of the mountain that's surrounding the landmarks, which in this case will be the support vectors. So we have two hyperparameters that we would like to consider. So we can try a whole bunch of these. So we'll set aside some values for these. So maybe we'll try C being like 10 to the minus 2, or 10 to the minus 1, or 1, or 10 squared. So there are 4 possibilities there. And then we'll try a bunch of gammas. We'll try gamma being, you know, 10 to the minus 2, 10 to the minus 1, and 1 or something. So now there's 4 times 3 is 12 possibilities. And now for each choice, we have this model H C gamma, and we evaluate this using cross-validation on the training set. And so each time we do that, we get some error score, right? We get like the score of C and gamma. So that can be like error or accuracy or something like that. So let's assume that higher is good. So then we pick the best parameters. So like the final parameter choice will be C star gamma star, and so these will be the C and gamma that maximize the score of C and gamma. Okay, and now we have sort of the winning hypothesis class here is C star gamma star. So now that we have that, what do? So we use C star and gamma star to as our hyperparameters. And now we train on all of X train. So that hasn't happened yet. We've been doing we use cross validation to select these parameters, but now we're gonna train on all of X train for C star gamma star, and that's going to produce some best hypothesis. Let's call it G star. And now we can use the test set to approximate the out-of-sample performance of G star. So use the test set to approximate the out-of-sample error of G star. And now we have our, so this will be our out-of-sample estimate. If you were doing this in a real production environment, meaning like if this were your job or something, what you would do now is, so you take this to your boss. So you say, I have a model and it performs this well. So this is how well my model does. So you provide this as an estimate of out of sample performance, but now you retrain on all the data you have. Using, so this is the full data set using the best hyperparameters, C star and gamma star. And so this gives you some final model, I don't know, let's just call it G here. And now G is what you use in production. But the performance of this G will be even better than the performance of G star. Why will that be true, or probably true? How much of the data did G star get to train on?
Just for the train test split.
Yeah, exactly. So G star only got to train on 80% of the data. So it had this out of sample error, but that's the out of sample error it had when it got to train on 80% of the data. So if you get to train now on 100% of the data, then your hypothesis is going to be even better. So this is sort of like, I don't know if you can mathematically prove this is true, but it makes sense that the out of sample error of G is going to be even less than the out of sample error of G star. So this is still the best estimate that we can do. But the client or your boss or whoever is very likely to be pleasantly surprised because the true performance of the model after you're able to retrain on the entire data set is probably going to be even better than the best one that you were able to produce with an error bound. Okay. So that's a validation set. You know, validation set is used for selecting hyperparameters, and we did it with leave one out cross validation. Usually the way people do cross validation is not leave one out. It's for example, let's look at 3x cross validation. By the way, the Wikipedia article has a great graphic, like a GIF or something. So with 3x cross-validation, first you leave out 1/3. Is that 1/3? Not quite. Okay, so you leave out 1/3, and this will be sort of like the test, and this will be the train. And then you get a certain performance score. So let's say that this is like 84% accuracy or something when you do this. And then you, instead of, now you leave out the middle third, and now this becomes the test set. And this becomes the training set. And this is also the training set. And so you do this and you get a different performance. Let's say you get 80% performance when you do that. And then finally you leave out the last third. So this assumes that, you know, this X train has been shuffled. Otherwise this wouldn't be good because the probability distributions might be different on these 3 different segments. But now this one will be the test, and these 2 will be the train. And let's say that you get like 82% this time. Then your estimate for out of sample error would be the average of 84, 86, and 82. Okay, and so whatever that is, can you guys just figure that out? It's 84, right? So this is actually 84. Okay. So your evaluation of these particular hyperparameters using 3x cross-validation is 84%. And then you would try other hyperparameters too, and whichever one gave the best average performance across all of the folds of the cross-validation would be the best hyperparameter set. So it's more typical to use 10 than 3. Like let's go here and we'll just look at the Wikipedia article on cross-validation. And they have this nice graphic here. Oh, here it is. Yeah. Whoops, it's too big. Can you guys see that well?
Yeah,
so
we
good. So this is in fold cross validation where n is equal to 8. So now you have this shuffled training set, and you just 8 times you leave out 1/8 of the training data, and then train on the rest and predict on the leave out set. And then you average all of those 8 numbers, and that's your 8-fold cross-validation score for the hyperparameter that you're considering. So you do that for all the hyperparameters, and then the hyperparameter with the highest cross-validation score is the one that you retrain on the entire training set, and then send that guy up to the test set to get your out-of-sample error. And then you show that to your boss, and then if you're in a production environment, then you retrain on the entire training set. And then that final hypothesis, we don't have an error estimate for it, but presumably it does even better than the one that only got to train on the training set. Okay, so we got through a lot today. I hope it wasn't too fast there at the end or too disorganized. But does anybody have any questions on cross-validation? Okay. So if anybody wants to meet tomorrow, I'll be in this room at 10 a.m. If nobody shows up, I'll leave. But I'll be here at 10 if anybody wants to come by. Let me do the attendance really quickly and stop the share here and open the this and stop